Variational quantum eigensolver is a hybrid algorithm that uses both quantum and classical computing techniques. The main goal is to find the ground state energy of a given Hamiltonian, which is analogous to finding the minimum of a cost function in classical optimization. In the context of the variational quantum eigensolver, VQE parameterizes quantum circuits per a trial wave function, ket psi theta. The goal is to approximate the ground state energy of the Hamiltonian. The VQE algorithm optimizes the parameters theta to minimize the expectation value, thereby approximating the ground state energy. The VQ algorithm seeks to find the ground state energy by minimizing the expectation value of the Hamiltonian for a trial wave functions. So the circuit is shown in the slide is a part of hybrid quantum classical algorithms called the variational quantum eigensolver, the QE, used to find the ground state energy of Hamiltonian. In this circuit, a quantum state is prepared to use a series of rotations, r sub x of pi, r sub y of pi, and r sub z of pi, which rotate the qubit around the x, y, and z axis, respectively. The quantum state is then measured, and the result is recorded into classical registers. A classical optimizer used this measurement to adjust the parameters of the rotation gate iteratively to minimize the cost function, thereby finding the optimal state corresponding to the ground state energy of the Hamiltonian. The equation that describes the relationship between the Hamiltonian and its eigenstate and eigenvalue is given by ket psi sub I equals to lambda sub I ket psi I. The eigenvalues lambda I sub I represent the possible energy level of the systems, and the eigenstates ket psi I are the states corresponding to these energy levels. In the context of quantum measurement, the energy of the system described by the quantum states ket psi I will be the eigenvalue lambda I. The VQE algorithm seeks to find the ground state energy by minimizing the expectation value of the Hamiltonian for trial wave options. This equation is crucial for understanding the energy spectrum of quantum states, and it is a core stone of quantum mechanics and quantum computations. The expectation of the Hamiltonian H is equal to bra psi H ket psi. It gives the expectation outcomes of an energy measurement for a system in state psi. If ket psi is an eigenstate of the Hamiltonian H with eigenvalue E, then H ket psi is equal to E ket psi. So in this case, the expectation value is equal to the eigenvalue E. The optimization in VQE is achieved by iteratively adjusting the parameters of the quantum circuit to minimize the expectation value of the Hamiltonian. This is done using classical optimization algorithms, which evaluate the expectation values for different sets of parameters and update the parameters to find the minimum value. The process involves preparing the quantum state, measuring the expectation value, and using this measurement to guide the optimization. So in the optimization process or step, classical optimization algorithms is used to adjust the parameters to minimize the expectation value of the Hamiltonian. With reference to the VQ circuits, we apply 3 rotation gates Rx, Ry, and Rz to the initial states. For instance, Rx pi is the rotation operators around the x-axis by an angle of pi. It equals a combination of the identity matrix I and the poly-x matrix weighted by trigonometric functions of pi over 2. Ry pi is the rotation operator around the y-axis by an angle of pi. It equals a combination of the identity matrix and the poly-y matrix weighted by the trigonometric functions of pi over 2. And finally, Rz pi is the rotation operator around z-axis by an angle of pi. It equals a combination of the identity matrix I and the poly-z matrix weighted by the trigonometric functions of pi over 2. In order to measure the expectation value, we need to measure the expectation value of the poly operators z, x, and y. The expectation value of z equals Bure minus 0, z gets minus 0, and the expectations value for x equals Bure minus 0, hx, h gets minus 0. And then finally, the expectation value of y is equal to Bure minus 0, s dagger, hyhs ket minus 0. So in the context of the variational quantum eigensolver VQE algorithms, the process is repeated many times with different parameters for the quantum circuit. The goal is to find the parameters that minimize the expectation value of the Hamiltonian. So the expectation value of the Hamiltonian Hitch is equal to A times expectation value of I plus B times expectation value of Z plus C times expectation value of X plus D times expectation value of Y. Using gradient descent in the context of the variational quantum eigensolver VQE require calculating the gradient of the expectation value with respect to parameters of the quantum circuit. This is often done using a technique called the parameters shift rule, which allows us to estimate the gradient by evaluating the quantum circuit at slightly shifted parameters value. Gradient descent and optimization algorithm is in machine learning to find the optimal value of parameters that minimize the functions. The partial expectation value of the Hamiltonian hitch with respect to theta I is approximately equal to the expectation value of h evaluated at theta I plus pi over 2 minus the expectation value of h evaluated at theta I minus pi over 2 divided by 2. And theta L is updated based on the following equation. Theta I minus alpha times the partial expectation value of the Hamiltonian h with respect to theta I. The expectation value plot shown in the figure provide a visual representation of the optimization process in the VQ algorithms. It shows how the expectation value of the Hamiltonian decreases over iterations, indicating the effectiveness of the gradient descent optimization in finding the parameters that minimize the energy. The curve shape with its initial rapid decrease, followed by gradual convergence and stabilizations, reflected the typical behavior of gradient-based optimization algorithms. And toward the end of the iterations, around iteration 60 to 100, the curve flattens and stabilizes mirrors minus 0.1. This indicates that the parameters have converged to the value that minimize the expectation value of the Hamiltonians, and further iterations result in minor changes.